Welcome to our guide on mastering cross-tabulation tables in SPSS. This presentation will take you from the basics of creating simple tables to advanced techniques for uncovering multi-layered insights. We will cover the entire workflow, from understanding the underlying theory to interpreting the final output and visualizing the results. Imagine you are a marketing analyst trying to understand if a new ad campaign was more effective with men or women. A cross-tabulation is the perfect tool to answer this question by comparing the gender variable with a purchased product variable. To begin, let's frame the kind of business problem that cross-tabulation is designed to solve. This slide introduces a common business challenge where intuition clashes with data. The key insight we want to convey is that intuition, while valuable, is not evidence. Our objective is to transform raw observations into statistical facts. In this scenario, a retail manager suspects that higher income levels lead to greater PDA or smartphone ownership. However, simply looking at fluctuating daily sales counts can be misleading because the total number of customers in each income group varies. This gap highlights why raw sales numbers alone are insufficient. The solution we propose is quantitative analysis using cross-tabulation to determine if a statistically significant association truly exists between income level and PDA ownership. This allows us to move beyond simply asking how many to a more profound question: is there a dependent, statistically significant relationship? The choice of statistical tool depends on the measurement level of your variables. The central question is about the relationship between variables. When you are examining the relationship between two categorical variables, such as income group, low, middle, high, and owns PDA, yes, no, the correct tool is Crosstabs, which uses the chi-square test. If you are comparing a categorical variable to a metric or continuous variable, like gender and amount spend, you would use a tool like a t-test or ANOVA to compare means. It's important not to use crosstabs for continuous variables like age from 0 to 100, as the resulting table would be enormous and uninterpretable. You must group them into categories first, like 1825, 2640, and so on. The core of the cross-tabulation analysis is the chi-square test statistic, represented as chi-squared. It quantifies the difference between what we actually observed in our data, the O, and what we would expect to see if there were no relationship at all between the variables, the E. A large chi-square value suggests that our observed counts are very different from the expected counts, implying a relationship exists. Before we can trust the results, we must meet three key assumptions. First, the variables must be categorical. Second, the observations must be independent, meaning one person's response doesn't influence another's. Third, the sample size must be adequate, which is checked by ensuring the expected count in each cell is at least 5. If we are studying voting preferences, the independence assumption means we can't survey a husband and wife and treat them as two independent data points if one influenced the other's vote. Each observation must be a unique, independent choice. With the theory understood, let's see how to practically implement this in SPSS. To perform a cross-tabulation in SPSS, you navigate through the menu, Analyze, then Descriptive Statistics, and finally Crosstabs. In the Crosstabs dialog box, you'll place your variables. By convention, the independent variable, or IV, which is the presumed cause, goes into the rows box. The dependent variable, or DV, which is the effect, goes into the columns box. This setup makes interpreting percentages much more intuitive later on. If you have a third variable you want to control for, it goes into the layer box. We will discuss this advanced feature later. By default, SPSS only shows the raw counts, which can be misleading. We need to click the Cells button to add more information. Inside the Cells menu, it's crucial to select Percentages. Row percentages are the most common choice when the independent variable is in the rows, as this allows for easy comparison across categories. It's also good practice to select expected counts to check the sample size assumption. Next, we click the Statistics button. This is where we ask SPSS to perform the significance test. We must check the chi-square box. It is also highly recommended to select phi and Kramer's v. These statistics measure the strength of the association, which the chi-square test alone does not tell us. For our income and PDA study, selecting row percentages will show us, for example, what percentage of low-income people own a PDA, and what percentage of high-income people own a PDA. We can then directly compare these two percentages. Now let's apply these steps to our case study. Our case study uses the demo.sav dataset to investigate the relationship between income and technology adoption. The specific research question is there a statistically significant association between income category and owns PDA? To set this up, we move income category to the row box as our independent variable and owns PDA to the column box as our dependent variable. A crucial pre-flight check is to ensure your categorical variables are correctly defined in SPSS's variable view. They should be set as nominal or ordinal, not scale, to ensure Crosstabs treats them correctly. Looking at the raw counts, the middle income group has the highest number of PDA owners at 455. This might lead you to believe they are the highest adopters. However, this is misleading because the middle income group is also the largest sample in our dataset. The raw count simply reflects the sample size, not the relationship. When we look at the row percentages, a much clearer trend emerges. We can see that only 12% of the low-income group own a PDA, compared to 20% of the middle-income group and 35% of the high-income group. The rule of thumb is to always compare percentages across the categories of your independent variable. Here, comparing 12%, 20%, and 35% clearly shows that as income goes up, PDA adoption goes up. This is like saying more people get into car accidents in Tokyo than in a small town. It's not because Tokyo drivers are worse, but because there are millions more cars on the road. You need to look at the rate of accidents per 1,000 cars, which is a percentage. We can see a clear trend, but is this trend statistically significant, or could it have just happened by random chance? The chi-square test table tells us if the relationship we observed is statistically significant. We look at the Pearson chi-square row, and specifically at the asymp sig two-sided column. This is our p-value. The decision logic is straightforward. If the p-value is less than or equal to 0.05, we conclude there's a statistically significant relationship. If it's greater than 0.05, we conclude any observed relationship is likely due to random chance. In this output, our p-value is 0.391. Since 0.391 is greater than 0.05, we would fail to reject the null hypothesis, meaning there is no statistically significant relationship between income and PDA ownership in this sample. It's important to remember a key warning. Significance only tells you that a relationship exists, not how strong it is. In our case, since the relationship isn't even significant, discussing its strength becomes less relevant. However, for the sake of a complete analysis, if this relationship were significant, the next logical question would be, how strong is it? To measure the strength of the relationship, we look at the symmetric measures table. The specific statistic we use is Kramer's v. Kramer's v ranges from 0 to 1, where 0 means no relationship and 1 means a perfect relationship. For 2x2 tables, the phi statistic is equivalent and can be used instead. We can interpret the value of Kramer's v using these general guidelines. Less than 0.1 is negligible. 0.1 to 0.3 is weak. 0.3 to 0.5 is moderate. And above 0.5 is strong. This is a critical step for assessing real-world impact. A statistically significant result, a low p-value, with a very small Kramer's v, e.g. 0.05, means that while the relationship is real, it's so weak that it might be practically irrelevant for business decisions. In the output shown, Kramer's V is 0.050. Even if this result were statistically significant, a value this low indicates a negligible to very weak association. We have statistical significance, but not practical significance. So far, we've analyzed the relationship between two variables. But what if a third variable is influencing the results? This is where layering comes in. A layer variable, also known as a control variable, allows us to perform a multivariate analysis. It helps us check if the relationship between our original two variables holds true across different subgroups. The primary purpose is to detect confounding variables or interaction effects. A confounding variable is a third factor that influences both the independent and dependent variables, potentially creating a spurious association. Let's consider a scenario. Does the relationship between income and PDA ownership hold true for everyone, or does education level interfere? By adding a layer, we are essentially asking, is the relationship between income and PDA ownership consistent for people with a high school degree and for people with a college degree? For instance, perhaps the relationship between income and PDA ownership only exists because people with higher incomes also tend to have higher education, and it's actually education that's driving PDA ownership. Layering helps us untangle this. To do this in SPSS, the action step is to simply drag the control variable, in this case level of education, into the layer box in the Crosstabs dialog to control for its effects. When you add a layer, SPSS produces separate cross-tabulation tables for each category of the layer variable. In our example, we get one table for the high school group and another for the college degree group. We then interpret each table separately. We might find that the relationship between income and PDA ownership is not significant for the high school group, with a p-value greater than 0.05. But it is significant for the college degree group, with a p-value less than 0.05. This leads to a much more nuanced conclusion. Education moderates the relationship. Income only predicts tech adoption for those with higher education. This is a powerful, actionable insight for marketing, allowing us to target segments more precisely by understanding these interactions. Be aware of Simpson's paradox, a phenomenon where adding a layer can sometimes reverse the trend seen in the simple, unlayered table. Layering, in essence, allows for multivariate analysis within a simple table structure. To effectively communicate your findings, especially to non-technical audiences, a visual representation is invaluable. A picture is truly worth 1,000 numbers. Clustered bar charts are an excellent way to visualize cross-tabulation results. They can instantly show the differences in row percentages across groups. In SPSS, you can request these charts directly from the Crosstabs dialog by selecting bar charts under chart type and frequencies for chart values. The key is to perform a visual check. Look for how the ratios of the bars change across the different categories of your independent variable, as demonstrated by the income categories and PDA ownership chart, where the proportion of owns PDA changes from low to high income. This visual check helps to quickly identify trends and relationships. Here is a simple, 4-step checklist to ensure a thorough cross-tabulation analysis. First, scan the percentages. Look for visible patterns or trends across the rows or columns before you even look at significance. Second, check for significance. Look at the p-value. If it's not significant, greater than 0.05, your analysis usually stops here. If it is, you can proceed. Third, check the effect size. Look at Kramer's V to determine if the relationship is strong enough to be meaningful in a real-world context. Finally, for a deeper analysis, you can check the residuals, not covered in detail here, to identify which specific cells in the table are contributing most to the significant chi-square result. Following the checklist for our case study, 1. We saw a rising trend in percentages. 2. We found the p-value was significant. 3. We found the effect size, Kramer's V, was actually very weak. This structured approach prevents us from overstating the importance of our findings. For those who prefer efficiency and reproducibility, the entire process can be automated using SPSS syntax. Instead of clicking through menus, you can run analyses in SPSS using syntax, which is a simple programming language. The main advantage of using syntax is reproducibility. You can save your code and run the exact same analysis instantly on a new dataset next month, eliminating errors and saving time. The Crosstabs command has several subcommands: for results, for statistics, and for cells. For results defines the variables. For statistics requests tests like chi-square and phi, and for cells specifies what to display in the table, such as count, row percentages, and expected counts. A great tip for learning syntax is to set up your analysis using the menus, the GUI, but instead of clicking OK, click the Paste button. SPSS will automatically generate the corresponding syntax for you in the syntax editor. To conclude, cross-tabulations are a fundamental tool for uncovering relationships within categorical data. We've learned that by moving beyond simple counts to percentages, validating our findings with the chi-square test, and then refining our analysis using layer variables, we can uncover the true, often hidden, stories within our data. For those looking to dive deeper, we recommend the following resources: IBM